the thin line, blue, okay? And you can see the system what? From here, 0.15. Now over here, the positive amplitude means what? The system is at the bottom. Are we clear? Okay. And from here, you can see, do we have any oscillation? We don't have any what? Oscillation at all. Okay. So this is one of the response. Okay. Now, the next thing that we are going to do now, we are going to change something now. Okay. So for example, number 2, okay, for example, number 2, what we're going to do is, all right, the mass is still the same, 9.02 kilogram. The damper is still the same. However, we are going to change the stiffness, K, and we are going to change this to 1250 Newton per meter. Okay, we're going to change this to 1250 Newton per meter. Boundary condition is the same. So boundary condition is we have when time is equal to 0, y as a function of time is equal to 0.15, sorry, positive. And then velocity is equal to 0 meters per second. Now, some of you, if we were to go into our previous or on the Excel spreadsheet, okay, I'd like to highlight that on this condition, the initial condition you can change. If you change your velocity at time equal to 0 is 2 meters per second, you can see how your what system change also. Okay, so this is the response of your system at 2 meters per second boundary condition, but we are going to put it at 0. Okay, so play with it. Okay, don't just read textbook and okay. See how the thing respond and get you high a bit is always good. I get high when I see that, but I don't know about you. So the first thing again, procedure is exactly the same. We're going to check. Okay, we're going to check C squared and 4 mk amplitude. So we know C squared did not change, so this is equal to 40,000. Okay. And now when we formulate 4 mk, we got 4 or 9.072, and then we have a stiffness of 1250. So when we so now we have a case where this is 45,360. So when that's the case, right, we know, I'll let you guys finish writing first. So once you reach a condition like this, what we have is now is what? C squared is less than 4 mk, right? So I'll teach you how to remember what to do next, okay? So immediately you have your alpha value, which is equal to C over 2m. And we compute this before, right? So C over 2m is the same as what? The value for alpha C over 2m is equal to 11.023. Right? We compute earlier, right? However, now when we were to formulate beta, beta originally is equal to what? C squared minus 4 mk. Eugene, come on. And then we divide by 2m. And then when you put the values in, we know that C squared is 40,000. Minus 4 mk, which we have computed earlier, which is 45360. Okay, 45360. And then you divide by 2, 9.072. And you know that this is impossible. Okay, so in this analysis, what you tend to do is you call omega d. And now omega d is equal to 4 mk. Minus c squared divided by what? 2m. Okay. I tend to do it this way because help me remember that we have to formulate what? Omega d. Okay. So from here, once you flip it over, 45360 minus by 40,000 divide by 2 divide by 9.072. So now you get a damped nature frequency of 4035. 4.035 radians per second. So this is what we call omega d, which is your damped natural frequency. So we proceed by solving. Okay, so we know that from here, our general equation or general solution, y as a function of time, will be equal to E minus alpha t C1 cos omega dt plus by C2 sine omega dt. So we know the value of alpha. So E minus by 11.023t C1 cos. Omega t is 4.035 plus by C2 sine 4.035. Hey, 4 point, where got 40.03? Come on, Eugene. Okay. So also very straightforward. So next we are going to, so this is, I'll call this my equation number 5. We finish at 4, right? Let me see. Yep. Okay, that's equation number 5. So from here, we're going to put in substitute. We're going to use boundary condition number 1, where we have y as a function of time. The initial condition is positive 0.15 meters. So time is equal to 0 then, right? So by looking at that, when time is equal to 0, I will not skip step. I will show you briefly how it looks like. So E minus 11.023. Now time is equal to 0. C1 cos 4.035 multiplied by 0 plus by C2 sine 4.035 multiplied by 0. So you know this sine of 0 is equal to what? 0. This is equal to what? 1. So therefore, C1 is equal to what? 0.15. Okay. So you just need to differentiate. It's so straightforward. You guys were probably laughing at it now. Okay. So we're going to use boundary condition number 2. Where you have y when time is equal to 0, this is equal to 0 meters per second. So when you have this, okay, so what you need to do is we are going to differentiate. Okay. So this is equal to minus 11.023 E minus 11.023 T. Okay, bracket. So you differentiate what's outside first. Hold the inside constant. What rule is that called? Any idea? Anyone? Chain rule? I have not a clue. Okay, I'm telling you, that's what I'm asking. Okay, I only know the procedure. And then plus E minus 11.023 T. And then you differentiate inside. Cos to sine is minus C1 sine. Oh, no. It's minus 4.035. C1 sine 4.035 T plus by 4.035 T C2 cos 4.035 T. So I'm not going to do the substitution bit. You will solve it yourself. It's so straightforward. So from here, we just substitute C1 is equal to 0.15. Okay, and then we substitute this expression when time is equal to t equal to 0. So finally, you will have an expression. When you do everything, you get this expression. This is equal to 0 minus 11.023 C1 plus by 4.035 C2. I don't want to waste your time. Okay, you can check on your own later on. So from here, we now want to find what's of C2. So this is 11.023 multiplied by C1 of 0.15. And then we divide the whole thing by 4.035. And finally, our C2 will be equal to 0.4098. Okay. So therefore, our unique solution y as a function of time, what we have over here is equal to our C1 or E minus by 11.023 T. And then we have our 0.15, this is our C1 cos 4.035 T plus by C2 sine 4.035 T. 4.0. Oh, no, not this, not C2, Eugene. Wake up. 0.4098 sine 4.035 T. Again, this will only work when what? Time is equal to 0.15 meters. So this solution only works for this, okay? Now, if we were to then look into our Excel spreadsheet that we change. So now what we do is we enter the value. So mass is the same, damping is the same. We change our what? Stiffness. You don't see so much of an oscillation yet, but you can see what? If you look at the unique solution, okay, so this case, the first part of the solution, this is invalid. Why is it invalid? C squared minus what? 4mk. Yes or no? Okay. So there is oscillation. So if we were to increase our stiffness to 2000, can you see what's happening? Okay. When is there an oscillation is what we call over here, right? You can see this, there's a what? Overshoot. Okay, it's not stopping at 0, it's going more than 0, then it's going to come back. Are we clear? Okay. I will post the homework on Wednesday. Okay, if that's not the case, I'll see all of you on Wednesday.